In this video, we have a more complex mechanical energy problem. What we've got here is a hill. Let's say this is a roller coaster. And the roller coaster is going to go down the track. It's going to hit this valley. It's going to be its lowest point. So we're going to solve for the velocity at its lowest point, when all of the energy is kinetic energy. And then it's going to hit this second hill. It's going to hit it fast. It's going to go up to a height of 10 meters. What will its velocity be at that point? And what radius must that hill be at minimum in order to prevent the roller coaster from flying off of the tracks? Because if that hill is very tiny, then that roller coaster goes up it and then jumps it. And then we're going to have a loop-de-loop. And I want to know, what height and radius must this loop-de-loop be in order to stay on the track once again so that it doesn't fall? At both of these spots, let's use pink to identify where we're making our free body diagrams. At both of these spots, we're going to have a couple of forces. So this is our spot 1. First spot, we're going to have the force of gravity going down. And then we're not sinking through the track, so we're also going to have a force normal going up. Now, what would happen if our force normal was less than 0? That would mean that the track there's no longer any contact force between the track and the roller coaster, which means that the roller coaster would go off of the track. It means it would fly off the track. We don't want that. So our force normal must be greater than 0. Now, this becomes a centripetal force problem because this is a circular motion. It's following a circular path. So force normal must be greater than 0, which means that my force of gravity and my force normal would really both be good placeholders for my centripetal force, because they're both going to be equal to the same thing. Ideally, my force of gravity is going to be my maximum, and it's going to be equal to mg. So I can put mg here, and then my force centripetal would be mv squared over r. So that's what I'm going to have at this point. At point number 2, I'm going to have force of gravity going down, and that will also be my centripetal force. But this time, if I'm not moving fast enough, then my force normal won't be there at all, and I'll just fall off the track. I'll fall straight down. And so in the same way, this must be my centripetal force. So I'm going to have mg equaling mv squared over r. Now this velocity will be this velocity, so we'll call that v3. This will be v3, and this will be v2, and this will be v2. Now, we'll be able to do some substitution here to solve these. But let's first warm up by solving for the velocity at the lowest point. When I first start on this track, I've got a total mechanical energy, right? We could write that in. I could say my total mechanical energy would be equal to my potential energy plus my kinetic energy. Well, at the top of the track, we're going to say we start at a velocity of 0. Is that a good 0? That looked like a 6. A 0. So my kinetic energy will be 0. So all of my mechanical energy will be in the potential energy. It will be locked away in the height. And so my opening equation is mgh. And we're going to say h1. And h1 is equal to 25 meters. Yeah, 25 meters. And so we're going to have that equal to our first kinetic energy. When our height is 0, our kinetic energy will be maximum. So it'll be 1/2 mv squared. The nice thing is the masses will cancel out. In each of these problems, our masses will cancel out. So then I just have a 9.8 times 25. That'll be equal to 1/2 v squared. And so I can multiply both sides by 2, and then take the square root, and that'll get rid of my 1/2, and that'll get rid of my square. And so I can run that calculation to get the velocity. And so my velocity will be 22.1 meters per second. V1 is 22.1 meters per second. Okay? Nice little warm up there. We should be pretty good at that now. 22.1 meters second. But what about this second moment? Well, at this second point, my mechanical energy is going to be split between potential and kinetic. I'm going to have some potential, some kinetic, but it's all going to be equal to that initial energy. So it's going to be mgh1 being equal to the addition between 1/2 m v2 squared plus mgh2. Once again, my m's cancel out. My masses all divide out because it's the mass of the same object. I get that same 9.8 times 25. And this mgh becomes 9.8 times, what do we say, 10? 10. And still I get 1/2 v2 squared. Now, before I go any further, I want to consider, what about that centripetal force? I could solve for my velocity right now, but what about that centripetal force? That is going to be found using this equation right here. And so let's write that down next to our work. So we're going to have mg equals mv squared over r. There are a couple of ways that we could solve this. The first way is I could just solve for my velocity over here, and then I could substitute that number in right here. Or I could rearrange this equation and substitute that in over here. Let's look at both. So first, I'm just going to solve for this velocity by calculating my two numbers. All right, when I put these together, then I'm going to take my 245 minus my 98. That's what I did over here. I end up with 147. I multiply both sides by 2 to get rid of my 1/2, which gives me 294, and then I square root both sides to get my v2 all by itself. And I get 17.1 meters per second. And so now I'm going to plug that in for this v right here. In this problem, my masses also cancel out, and so I'm left with g equals 17.1 squared over r. And I'm solving for r. So let's move r to the other side, and let's bring g down underneath. And so we're going to have r equals 17.1 squared divided by 9.8. We can solve that. And so my r equals 29.8 meters. So my radius has to trace an arc of 29.8 meters. And so I said we could substitute this in instead. So if we go back to, let's do this step right here, before we substituted any numbers in. If I set that up, I've already eliminated my masses. I've got GH being equal to the addition of 1/2 V2 squared and GH2. But then I can set up my pink equation over here. That's going to be G equals V squared over R. I can multiply both sides by R and end up with RG equals V squared. Well, this V squared is this V squared. So I can take everything equaling this guy and plug it in right there. And so I could say now what's nice about this way is my gravities cancel out as well. And I end up with H1 being equal to 1/2 R plus H2. And so I can solve the problem that way as well. And that becomes a pretty simple problem. And I could replicate that problem. If I was designing a roller coaster and I needed to look at multiple waves, I could reuse this equation over and over again. So it becomes useful to be able to derive custom equations like that, especially when we're doing some designing work. Now, that's how we solve for the radius here and the velocity here. But what about this velocity and this radius? Well, this one, there's going to be a little trick, because this point right here, this will be our height. So that'll be our h3. and that will be equal to twice that radius, because this is a circle. This is a good circle. And so the height must be the diameter of that circle, which the diameter is 2 times the radius. So we can set that up as well. And so we're going to have the same setup that we had before. Okay, let's go ahead and eliminate all of our masses right away because they all cancel out. They all divide out of each term. And then, since we have an unknown velocity and an unknown height, let's do some substitution. Let's set up our centripetal force equation so that we can substitute it in. And since that's going to be the same green v squared, let's use a green. And then that, which is that, substitutes in for that. And now my gravities all cancel out, and my H2, remember, that's equal to 2r. That's this same r. And so I can substitute that in as well. And so let's eliminate our g's, and then substitute my 2r in. And now I can, these are the same term, r and r, so I can add these together. And now I get my height will equal 2.5r. My height was 25, so I can divide that by 2.5. That will give me the value of r, which should be 10. So r will equal 10 meters. And now my height was 2 times that r, so I can say my height, my h3, will equal 10 times 2, which is 20 meters. I can now also plug this back in and solve for my velocity. And let's actually do that. Let's do that right here because that'll be the easiest spot. Because that's going to be 10 times 9.8, take the square root, and that'll give us v. And so my velocity becomes 9.9 meters per second. So these problems look really intimidating, and they can be challenging to set up. But once we set them up, if we can just remember our conservation of energy and keep in mind some of the other tools that we've learned, like centripetal force, we are able to actually solve these very simply.